Hi, Mark. Nice to meet you.
Good to meet you. Thanks for having me.
Fantastic. I'll let you start off by introducing yourself and your journey so far in the tech and energy industry.
Well, it's too long a journey at this point in my life to spend a long time on, although I'm easy to find on the magic Google machine. So I would say from the viewpoint of my journey, as you put it, there's the personal and professional side. But I began life as a physicist. That's what I studied at Queen's University in Canada. And I did work as a scientist for a period of time and as an engineer. My first job was as an engineer because I couldn't get a job as a physicist when I graduated. There weren't many. But I was lucky. I ended up working in semiconductor manufacturing as what's called a process engineer, large scale integration. Terrific experience in a fab. Went from there into guidance devices, optical detectors for anti-missile systems, and then into lasers. And then I got involved in the commercial nuclear industry in Canada, the Canadian uranium refiner and mining company, which today is called Cameco. In my personal orbit, I'm the only person that's been to the bottom of I think a 6,000-foot vertical hard rock shaft in granite, which you could do in Finland or Sweden and northern Canada. But I went from there to the United States in the nuclear industry and arrived in that country as a young man, just in time for the accident at 3 Mile Island, where I spent the week of the accident at the accident site and spent the next close to 10 years of my life defending the virtues of nuclear energy because it's important. Obviously, I failed because most countries abandoned their nuclear programs, except notably Russia and China. I consulted to the Swedish nuclear industry 1 year after 3 Mile Island as the resident expert who had been at 3 Mile Island because Sweden at that time had a national referendum to decide whether the citizens really wanted to abandon nuclear energy. They voted to abandon it, but the vote was to abandon it 30 years later. So as a consequence, they didn't shut the reactors down wisely, and 30 years later, they just ignored the ban, and the legislature rescinded it. And then I was fortunate in the sense I was in policy and politics in the sense that I, as a young man, worked in the science office at the White House under President Reagan. In the United States, it's unlike Canada, and I think unlike most parliamentary systems, you have a system of personal advisors that are in offices that are similar to advisors in parliamentary system, but a little more formal here. So the Office of the Science Advisor is a specific office created under President Kennedy because of that time, the advent of nuclear weapons and the concerns of having the president get unbiased advice on science and technology as opposed to political advice. That was the purpose of such an office. And so it was good to be in that, but it's also political policymaking realities. It was more fortunate than I realized for me to have that experience, because then you saw how science and technology intersected with policymaking and politics, which matters. As a trained scientist and former engineer, I have a few patents from the days I used to do real work and build things with my hands. Politics matters. Politics matter enormously. It's not that scientists want to be remote from politics. They can't and shouldn't be. In their personal life, politics matter, but it matters very much to businesses, obviously. And that was a great education for me, a great gift in a sense. I went into consulting, worked with hundreds of utilities, because in the United States there are hundreds of electric utilities. Worked in the oil and gas industry, co-founded a tech venture fund, helped take a company public as founding chairman, CTO, that made detection technologies. Let's see bad things, chemical, biological, radiological, nuclear threats, explosives. That was post 9/11 for obvious reasons. That's why we birthed that company. Then I got involved with public policy world with the Manhattan Institute, worked there for a decade as a senior fellow, writing about energy and technology policy, about robotics and computing, about jobs, automation, about nuclear energy, about oil and gas, about fracking in the shale fields, testified before the U.S. Senate and Congress many, many times, written what I hope are influential policy papers looking at the science and technology and economics of big questions like what kind of energy sources should we use? Would it make, can you have an all electric world? Can you have all electric cars? How do you make batteries? And I worked as a consequence of my involvement in venture with a lithium battery factory, which is not in my resume online, but I think it might be now. I've added this back. I was chairman of the factory for a while, small factory in the United States. We had licensed technology from China, the very popular lithium iron phosphate chemistry before anybody had ever heard of it. So I ended up running that factory for almost a year as interim CEO, which of course meant that I learned more about two things, and I preferred to learn battery chemistry. I wasn't eager to become more knowledgeable in battery chemistry, but I did. And of course, the challenges of an early stage manufacturing company, which I was, CEO of briefly. We succeeded technically. We failed in a business sense. And we failed in a business sense largely because of subsidies that were coming into the market at that time that distorted the market and made it very difficult for new technologies to compete. So since then, I've co-founded a couple of organizations, but maybe the most important one that I founded this year. I left the Manhattan Institute, where I still have an affiliation as a editor, a writer for their terrific journal, the City Journal, for those of your listeners and viewers who want to understand what's going on from the right of center perspective in the United States, the intellectual thought across the subject area. I write technology and energy column, but I write a monthly column there, mostly about energy, but also about technology, robots, and automation. But I collaborated with a Texas think tank. In the United States, we have big states with big policy think tanks. As you know, many of the states in the United States are bigger than countries, both in geography and in economic terms. So Texas is a country in energy terms. It really is. I think it's probably the fourth biggest energy producer in the world if it were a country. So Texas is a state of consequence in the energy world. They have a think tank, and they collaborated with me and seed funded a new energy think tank, a national energy think tank with global aspirations called the National Center for Energy Analytics. And I created that as its executive director. It's brand new because there isn't, in the United States at least, an independent, not independent intellectually, but I mean independent of a corporation or independent of a university. There is not a significant independent energy think tank. So that's why we created it, to do analysis and scholarship on these issues that are obviously important to every country. It's no longer a backwater issue. It matters to everybody, whether you're in the environmental community, the geopolitical community, if you're the economist, and if you're a tech company. And as you know, the news, which is not news for me because I've been writing and studying about the energy appetites of the digital world for 25 years. But the news to the rest of the world is to discover that the cloud, the most important and biggest infrastructure ever built by humanity, the cloud is the world's biggest infrastructure energy consumer, bigger than aviation, growing faster than any other infrastructure. And I would say, for all practical purposes, with no end in sight in terms of realistic timeframes in its expansion. So that's a long introduction, but it helps you give you a sense of, I come at things from the three domains of technology and science, policy and economics, because at the intersection of those three things, that's where the real world happens.
Absolutely. And we're going to go deep diving on those subjects even more. So okay. I'll start off with a banger quote from your last keynote speech from YouTube. So you had a quote that was really, really interesting, and it was, "There is no energy transition." Can you explain that a bit more?
Yeah, sure. It sounds provocative because of the importance that the phrase energy transition has adopted in the political spectrum. But I'm a data guy and a science guy. And I think words matter. I think precision of words matter. So we know what the word transition means. It means you go from one thing to another. So if we look at the data in terms of how the world uses energy, and of course this is a global discussion. It's true for Europe, but my statement pertained to the world. The data show there isn't any energy transition going on, and nor is there an accelerating energy transition going on. And that's just a statement of fact of where we are. The more provocative point, which is a forecast, is my claim there won't be one, which requires more explanation than the fact that there isn't one. And the reason there isn't one, we just look at the data. If we look at the percentage of the world's energy coming from hydrocarbons, oil, gas, and coal, 20 years ago and today, this is not complicated accounting. It's in the International Energy Agency. It's lots of places. There is a diminution in the percentage of all the world's energy supplied by hydrocarbons in the last 20 years. The percentage. It was about 84% 20 years ago. It's about 82% today. So a 2 percentage point reduction. But over that 25-year period, the absolute consumption of hydrocarbons has increased. And in energy equivalent terms, it's increased by an amount equal to 6 Saudi Arabia's worth of oil production. So the absolute consumption of hydrocarbons has risen. Its percentage share has declined. I would use the adjective trivially. 2 percentage points is not a lot after, give or take, depending how we count the spending in Europe and the United States. Let's say $1 to $2 trillion deployed to avoid hydrocarbons has led to barely 2 percentage point change, but the absolute consumption of hydrocarbons has gone up. At the same time, the absolute consumption of electricity from windmills, from solar arrays, electric vehicles have expanded. All those have expanded. So the pattern of the last 2 or 3 decades echoes the pattern of the last 200 years. All forms of energy expand, including coal and including wood. This is the surprising thing. So when I did a little digging, a lot of the energy agencies that track energy data are a little sloppy about the tracking of biomass, including it in the macro data. Europe data is pretty good on this because biomass, whether it's peat or wood co-fired with coal, whether it's biomass used to make alcohol, synthetic liquids, they're pretty good at better than the United States, I would tell you. But I can tell you for a fact that the world's consumption of wood as a fuel source is higher today, not lower. In fact, in absolute terms, the world provides more energy burning wood than it does from all the world's wind turbines and solar arrays combined. Not more, but 2.5 times more, 250% more energy supplied by burning wood globally than from the production of electricity from wind turbines and solar arrays. That's just a statistical fact. It seems shocking. The point of those numbers is, I would say, to be sort of facetious, when wind and solar beat wood, then I would say the world has transitioned from wood to more solar and wind. But the wood won't go away. Wood is going to shrink somewhat in absolute terms eventually, and wind and solar will rise. At this point, the data show no transition. What the data show are additions in absolute terms. And what the future will likely hold is the echo of the past, because the economies require energy, and they require it in different forms for different reasons, whether political or regulatory or practical. We'll see an expansion of all. We might artificially accelerate the expansion of electric vehicles, wind and solar, and nuclear power. That's a political decision. But we won't, in my opinion, see any diminution in the expansion of oil, gas, and coal either for a very, very long time. Now, it doesn't mean never. If you wanted me to forecast for a century, we can have that conversation. But a century is sort of irrelevant except as an interesting intellectual, philosophical exercise, right? The narrative around the energy transition is by 2030 or 2050, having a radical reduction or elimination in some people's minds in the use of hydrocarbons. I'll say one last thing sort of as a statistical fact. It's not just that hydrocarbons anchor the world's energy supplies, both directly and indirectly. Even Sweden and in Norway, for example, where Norwegians infamously are the biggest consumers per capita of electric vehicles, they're also consuming, and they've exported their consumption of diesel fuel to the countries that mine and refine the minerals to make the batteries for those cars. It's self-evident once you state it, but you want to put that into the accounting. And very few people are putting that into the accounting. And as I pointed out to my Norwegian friends when I was there last year, that every Norwegian buying an EV has already, by virtue of their purchase, before they drive the EV, regardless of where they drive it or if they drive it, emitted somewhere between 30 and 60 tons of CO2 just to purchase that EV. And the range, of course, comes from the uncertainties and knowing exactly where the minerals came from. 100% of everything in modern society, not 80%, 100% of products and services are dependent directly or indirectly on hydrocarbons. You don't build wind turbines without using hydrocarbons. There are no pharmaceuticals without hydrocarbons. There are no electric vehicles without hydrocarbons. So the state of play, never mind aspirations, is that there's a zero diminution and zero transition away from hydrocarbon dependency as a practical matter in the data over the last 2 or 3 decades. So that's why I say there is no energy transition.
It's more of an addition. And I checked your previous interviews, and there was one statement. There were statistics that said that the Tesla it proves to be ecologically viable after 60,000 miles. So you need to know what car it is, and that was It's
roughly, it varies depending, as you can imagine. There are variables with respect to the carbon dioxide burden to make the vehicle. It varies, depends where the aluminum comes from. As a statistical fact, 2/3 of the world's aluminum is produced in China. And that is on a coal-fired grid because the coal-fired electricity is cheap. Europe produces some aluminum, and certainly the Nordic countries have some production on hydro. That's what Canada does. But you'd have to document your supply chain that 100% of your aluminum came from that source, which is very difficult to do. Not impossible, but then you have to follow the copper supply chains, the nickel supply chains, the cadmium supply chains, and the neodymium supply chains. All of them trace to hydrocarbons. Then how you use the vehicle will determine how much hydrocarbons you use when you recharge the vehicle, and that varies not just by country. This is where I would call it intellectual dishonesty comes in saying that EVs cut CO2 emissions. You can't take an average on the grid to say this grid on average uses this many hydrocarbons to produce a kilowatt hour of electricity. The averages are irrelevant. What matters is exactly when and exactly where you plug the vehicle in on that grid at that time of the day or night. Those are the electrons that you're using, and the emissions from those electrons are what matters in the real world, as opposed to the hypothetical world of average calculations. So I mean, just as an order of magnitude, when you buy an EV versus a conventional vehicle in Europe, roughly speaking, your efficient diesel will have a lower carbon footprint for the first 60,000 miles. Some places it might be only for 30,000, and other places it could be 100,000 miles, or nearly. Maybe I should be talking kilometers. I grew up in both units, but
both units are perfectly fine. So if we then, you also said that everything needs energy, and I'll add to there that everything needs energy and logistics. So if we look at the logistics and the transition that's not happening, how do you see the decade going on regarding operating and building the supply chain?
This is, you put your finger on the most important economic and geopolitical and environmental feature of energy. It's the logistical supply chain that is entailed in delivering the energy service, the mile of driving, the hour of flying, the hour of compute time. And behind that, there's a network of logistical supply chains. One is the delivery of the energy itself. The other is a logistical supply chain to make the energy system itself, right? And then there's the logistical supply chain to provide the fuels to make the energy system itself. So that's sort of like a network of networks, because you've got to if you go in the other direction, right, you have to mine. All energy systems, doesn't matter what they are, require you start with a mining of materials to make machines. All of them. Everything involves building machinery. That involves a supply chain. You want to know who's doing the mining, how you get it to people. Is it shipping? Is it by physical ship, truck, rail, even air? All that uses fuel. The environmental feature of that, of course, is extremely complex. The language and the climate world is quote scope 3 emissions, which are practically, in all practical purposes, impossible to document or certify, just because the world's complex, supply chains are complex. But the geopolitical part of this is one that is starting to become obvious to people. So if you think about the two narratives, the transition is about primarily reducing the use of oil, but it's really, in the broadest sense, it's oil that people are most concerned about in the politics. It's always about oil. And there's a really good reason for that. 98% of all the goods in the world and all the human transport in the world, it's oil fired. Oil. Most of the rest is not electricity, it's biofuel. So of the 2 percentage points left that are not hydrocarbons, 1.5, 1.7% of it are globally are biofuels, and then the other 0.5% is electricity. So you move goods and people burning oil. It's just the way the world operates, and has for a long time, and will for a very long time. But set aside the forecasting. So you think about that supply chain at the primary end. The world worries most, for a long time, about the Middle East and about OPEC and Saudi Arabia. And so you worry in supply chain sense about resource concentration. What percentage of the world's oil is supplied by what percentage of the world's suppliers? And we know about what the supply concentration is. It's heavily OPEC, Russia, and the United States. Those are the three big dogs in global production. In the energy transition favored technology world, which is mineral dependent, mining and minerals, refining and minerals, the resource concentration, people know this by now, I started writing about it years ago, is China. The mining and resource concentration is Africa, and the mineral refining resource concentration is China. China's resource concentration in supplying the energy minerals to the world is more than double the oil resource concentration with OPEC. So from a practical perspective, if you're a geopolitical analyst, this is a red flag. I mean, you really worry, no pun intended, about the communist Chinese red flag, but it is a red flag, because so far it would be fair to say the resource concentration the Chinese enjoy, again, more than double OPEC's resource concentration. They have not exercised pricing power, nor have they exercised geopolitical manipulation overtly with that. I mean, OPEC's famous embargoes, right, of 1973, 4, and 79, was an exercise in geopolitical power, and their price manipulations, through OPEC, are an exercise in pricing power, obviously, and it affects the world. Everybody reacts when OPEC gathers and talks about oil prices. There's no equivalent events yet in energy minerals, but I think I would have to say it would be profoundly naive to think that'll never happen or might not happen. It's the nature of the conflicts in human affairs. So I've, personally waved red flags on this, and many analysts are equally concerned about that kind of concentration. So the idea that you're insulated from the OPEC oil, let's say Qatar natural gas, because you use solar arrays instead of gas turbines. Well, the solar arrays require batteries, grid scale batteries. These are all mineral dependent. You trace the resource concentration. And it traces back to a handful of countries dominated by China. And where the country primary supplies are in Africa, you find Chinese money and Chinese mining dominating that ecosystem. That supply chain is complex. It's geopolitically fraught. It's not an easy supply chain. It's not trivial to figure out where, say, an atom of copper that's in your electric car came from. You can't label that atom of copper. There's no way to tag it. That's not true. You could make it radioactive. I mean, just to be a pedant as a physicist, if you could tag it with radioactivity, and then it's really easy to track. But most people don't want their electric motors to be radioactive, so that's not what we're going to do.
But we want to move stuff anyways in the U.S. We need to get electric equipment, food to Walmart and all over the place. We need to have new kind of semi trucks on the roads. We need electric fueling stations, maybe also liquid biogas, you name it. Like how does that look like if you compare it to the regulations that you're having in the US and the addition moment that's going on?
Well, So the United States is a more difficult environment for transportation to electrify. I mean, U.S. is after Brazil has the largest biofuel market for transportation in the world, right? It doesn't nobody the only one that's close is Brazil and ethanol. I mean, the United States now grows more corn to run cars and than for food, because it's a big country with a very productive agricultural sector, so we can afford to do that. So, as you know, roughly 5% of U.S. gasoline, and there's those who like to take it to 10%, is co-mixed with ethanol. It's easy to distribute at that level. The chemistry of putting ethanol in gasoline is pretty easy. It has some issues, but they're manageable. But as you try to push that harder, you get into a lot of supply chain logistics and cost problems. So the holy grail, as you know, in the liquid fuels market is a biodiesel that is chemically plug replacement, right? Drop-in replacement to hydrocarbon diesel, and we're very close to that. Not quite there, but very, very close. As you know, it's been tested, doable. We also know that from a fundamental engineering economics perspective, it's about twice the cost of diesel. I'm not talking about the delivered cost with subsidies. I'm talking about the underlying engineering economics. And things like hydrogen you can use, underlying engineering economics are about 300% more expensive than just using CH4, natural gas, methane. So, but it doesn't mean you can't use it, and we won't use a lot of it because Europe and the United States are wealthy, and so regulators can pass laws that up to a point can lead to significant expansion in those markets, which is what's happened, and I think will continue to happen. But this is very different than a transition to all electric or all biofuel market. Globally, I would take the bet. I'd be happy to take a bet with anybody. Pick your time frame. This is not going to happen in time frames that have any meaning: 5 years, 10 years, 15, 20. But in specific environments, specific markets, specific countries, just relatively small geographic areas, you could affect a very significant transformation, a transition away from one class of fuel to another, even if it's more expensive, because people are pretty wealthy where you live and where I live, compared to much of the world, compared to all of India, most of China. So what I write about a lot is not the politics, although I have opinions and talk about the politics. When I write, what I try to write about are the limits to what the politicians are trying to do in any country. And the limits are defined by the physics and engineering of the systems that they're trying to regulate or mandate. So with respect to electric vehicle, for example, and liquid fuel vehicles, and again, let's set aside the cost difference between a bioliquid and a non-bioliquid. They operate thermochemically the same. So putting 10 gallons a second into a tank doesn't matter whether it's gasoline or diesel or biodiesel. Same flow rate. The nozzle weighs 6-7 pounds. It's on a hose. The nozzle. If you want to have an energy flow rate equal to that forget the battery. If you want an energy flow rate on the electric charger that you plug into a vehicle that could match the energy flow rate of that liquid, okay, the physical size of the electric cable is 10 times bigger. It weighs 10 times more. So to have again, set aside its cost. I'm just talking about the the physics. Now I'm talking about electricity 101 for electrical engineers. They look at the power flow and currents. You have a cable that's, about 10 inches across. The cable and its plug will weigh over 100 pounds. And the charger will have to be something on the order of 1 megawatt, as opposed to a few 100-watt electric pump that's in a gasoline biodiesel pump, as opposed to a typical fast charger that may be a couple hundred kilowatts. You're going to have to go to a megawatt. That megawatt in the supply chain requires different kinds of cable upstream, a different transformer, a very big transformer. So if you look at the physical infrastructure before you look at the cost, it's rather remarkable shift in the amount of material you need to affect the same service, an energy flow rate to a vehicle that's untethered. On the other side of it, you have to then look at the vehicle that you're putting the energy in, and these are just physics, electrophysics, and electrochemistry questions. How heavy is the vehicle to carry the same amount of energy? Well, we know the answer to that question. A gasoline fuel tank 80 pounds, diesel fuel tank, 80 pounds, what we do the kilos, but you call it, a couple hundred kilos. The battery contain the same amount of energy. A really good battery, whether it's a Volkswagen or Mercedes or a Tesla battery, it'll weigh half a ton. It's a lot. So that makes the vehicle heavier. So now I have to use more aluminum in the vehicle, which is what all EV makers do, which means I'm using more aluminum in that supply chain that's hidden from China, typically that's on coal-fired grids. So those facts are all knowable. They're not disputable. That's what a lot of my work is about, pointing out where the limits come in. So when people say, well, we could just subsidize, get more EVs. Well, yes, you can, but you have to ask, as you increase the number of EVs and you increase the need for on-road charging, you then have a cascading set of issues that are just built into the physics of the systems that have costs that are not linear. They don't just go up, say, double the number of chargers. They go up non-linearly because of practical supply chain operational realities. You can't, if you can't charge the vehicle and refuel it in 4 minutes, but takes 40 minutes or 15 minutes, I have to have more chargers. Otherwise, they create an inconvenience. You say, well, people have to put up with it. Okay, maybe they do. But that's a political and social and moral decision. It's that, but what I try to do is illuminate that you are forcing on people, you the regulators, a political, social, moral decision, not just an economic decision. I could subsidize it so its cost is co-equal, but it still takes me 5 times or 10 times longer to refuel on the road. And we can mandate that. Governments have a lot of power. Governments can simply say that's the way it's going to be. And of course, in effect, that's where we are in the energy debates. Governments have said a lot of that's the way it's going to be across the energy landscape. And a lot of the pushback that's now coming comes because of a combination of things like higher costs, inconveniences, lower reliability, especially in electric grids. These things begin to matter when they start to happen at scale. And so the reason I say there won't be an energy transition is not because governments can't, in principle, mandate that and increase all the features that they prefer. It's that I think there'll be a political pushback because the practical effect of those mandates is that it causes it to become obvious that the solutions that are promised and claimed to be co-equal aren't co-equal. That doesn't mean they're impossible. There's a different thing, right? They're not co-equal in a variety of ways. Again, cost, supply chain, environmental impacts. You're just shifting environmental impacts. You might reduce CO2. Let's say that a lot of things do, but you're going to increase water use, or you increase acidification of rivers in Africa, sub-Saharan Africa, or you increase the toxic use of arsenic in the mining because you have to use arsenic for many mines to dissolve rocks. So the absence of that kind of what I will call candid illumination of the underlying supply chain physics, supply chain economics, supply chain geopolitics is a serious omission on the part of the advocates, political or otherwise, for what they're calling an energy transition.
And what about, like, I remember you saying that we need a lot of steel mills, equivalent power plants to like the size of steel mills to build the infrastructure, and also like your book and what you spoke about a lot is that AI and cloud is going to bite a lot of the energy consumption.
Well, AI and the cloud give us the most obvious current example of a truism that sort of underlies a lot of my analysis and writing. It's that economic growth brings energy growth. And people's response is, well, we'll make the machines more efficient. And that way we can moderate energy growth. And my answer to that is yes, that's exactly right. Humans have been doing that for as long as we've made and invented machines. Engineers always make machines more efficient. But making them more efficient makes them cheaper to operate, which increases the use of those machines. It's called, it has a word that's been adopted because of the British economists of 200 years ago, the Jevons paradox, that increasing efficiency doesn't decrease the consumption. Well, that's because that's not always true. If you have no economic growth, no population growth, then you're static. You can increase efficiency and decrease consumption. But by and large, most machines are underused globally. There aren't enough cars in the world because most of the cars that are exist are serving the rich world, the 1.5 billion to 2 billion people who can afford cars. There's 5 billion people who don't have cars. That's a lot of people. So you could do the math. Imagine double the efficiency of every car, which is technically possible. But I'm going to triple the number of cars in the world. So this is the arithmetic. There'll be a net increase in demand, but not a decrease in demand for energy to run cars. The artificial intelligence and computing offer the purest example of the second feature of growth that I write about in my book, that it's sort of obvious what you stated. We humans create energy demands. We invent energy demands. The only underlying demand for energy is for survival, to food, fuel, and shelter. That's the only sort of essential demand for survival. Every other energy demand was invented. We didn't have demand for energy to fuel cars till we invented the car. There was no demand for energy to fly till we invented the airplane. There was no demand for energy for computing until we invented the computer. Then you need energy to make the computers and energy to run the computers. My proposition is twofold. Humans are far more productive in inventing demands than they are in inventing ways to supply energy. In the physics of the universe, there are very limited ways to make energy. But our imagination of different ways to consume energy, from entertainment to healthcare. Pharmaceutical industry is one of the biggest energy consumers in the world. The invention of pharmaceuticals was an invention of energy demand. But no one would say we shouldn't have pharmaceuticals and therapeutics. So the question then you would ask yourself, knowing that, is do we think that we humans have exhausted the possibility of all future inventions? And so as an archetypal example of that, I said, well, no one imagined the invention of a computer cheap enough and small enough that everybody would have one in their pocket. By everyone, I mean a lot of poor people in emerging economies have a computer in their pocket, the smartphone, that's more powerful than an IBM mainframe by a factor of 10,000. No one imagined that. Well, I shouldn't say that. Arthur C. Clarke imagined that in 1954, the science fiction writer. A couple of other prescient science fiction writers imagined, not many. Artificial intelligence was imagined in 1956. What no one imagined at that time, because they didn't think about it any more than when people invented the airplane. They thought about its ultimate energy demand. They knew it needed energy to fly. No one in the invention of the airplane calculated at that time the future demand for fuel to fly people in the world. We think about those things now because we consume so much energy. So I started calculating the energy appetite of computing some years ago and published a study in 1999. It was a very superficial study, deliberately, because there was very, very little good data. And it was titled "The Internet Begins with Coal," kind of a provocative title, to point out. And at that time, of course, in the United States, the primary source, the largest source of electricity supply was coal. Now it's natural gas, and coal is number two. In China, it's now coal's number one, 2/3, and natural gas is hydro, the number two. And the reason I did that was to point out that every computer has to be plugged in, which means it's plugged into a coal-fired power plant, one way or the other. And as you expand the number of computers, you're going to use more electricity. You'll probably use more coal in the near term, which is what happened. 10 years ago, I published another study called "The Cloud Begins with Coal," which you can still find at my website. If you Google "The Cloud Begins with Coal," you'll find the PDF. And in that, I predicted that the advent of the cloud infrastructure, which was very different than the internet, in an important way. The internet is a computer network that's mediated for communications between two endpoints. The cloud is the migration of the functionality of your computer services into a remote utility. It's a different thing, right? When my computer connects to yours on the internet, we're doing a communications function. The cloud uses that communications function, but it adds a utility function. It's, all apps are utility functions run in the cloud. So I pointed out that the cloud then became the fastest growing consumer of electricity in the world at that time. And I calculated then that it could use then more electricity than all the EVs. And I forecast at that time that 10 years later, the cloud would use 10 times more electricity than all the world's EVs that anybody imagined would be built. This was the dawn of the Tesla. And it turned out I was right. It's nice to be right for the right reasons. The number of EVs in the world is huge. There's maybe 10 or 15 million pure EVs. There'll probably be 30 million next year. in a population of 1,500 million other cars. But the cloud's growth is faster. AI, in energy terms, artificial intelligence, because AI software, the way it operates to learn and to do inference, requires that the computer doesn't cycle, it runs flat out. It's the equivalent of driving a race car or driving a semi-trailer. Automobiles, your personal automobile uses energy differently than a truck that delivers goods. Trucks that delivers goods are always being, their duty cycle, as you know, is very, very high. You want to run them at about 80 or 90% duty cycle, always moving. The only time they're not moving is to deliver the good and move again. An automobile is the opposite. It's 80% of the time it's just parked because of the social and economic value of on-demand transportation. I want it when I need it. It's in my garage or my parking lot.
Yep.
AI is more like a semi-trailer in the supply chain of compute. Your computer that you use in the old computer is more like your car. It's not being used most of the time. AI is roughly a 10x increase in energy use per square inch of silicon. And of course, we're building AI at a torrid pace, and it's already impacting electric demand for data centers. So data center electric demand is taking off. It's taking off because of the dual issue, because of the underlying utility of the cloud and the acceleration that AI brings to cloud utility. The analogy I used in a recent article, and I think it's good analogies, is, you're an engineer, you understand analogies are always weak, but they help you visualize things. I would say the addition of AI to cloud in energy terms, and then utility terms of how much value this cloud will have going forward, is the equivalent in the late 1950s of the advent of jet engines and changing global air travel from propeller-driven to jet-driven. In 1956, 57, there'd already been 40 years of global aviation. Global aviation was already a big industry. Air travel was already big. But if you draw the curve of air travel, it just took off, right, at the end of the 1950s because of practical jet engines that allowed cheaper, faster, more useful air travel. It's more useful if it's cheaper, faster. In the compute world, what AI is doing is making computing more useful. It doesn't replace compute function, but it makes a lot of the compute functions more useful. We're in the early days of that, but it's the equivalent of adding jet engines to airframes, adding AI to compute. And so I think we're at the end of the beginning of the compute era, and it's equivalent in aviation terms of the late 50s. And that has a lot of implications economically, geopolitically, strategically. For energy analysts, it has a lot of implications for energy use, which the tech community has just now woken up to. I think the experts who run the infrastructure know what I just said is true, but we'll call it the front-facing political class is sort of waking up to that.
Wow. So a couple of more questions before we call it a quits. So because I could go on for 5 more hours minimum.
I'll give you a short answers to the couple of questions so we could do the questions.
Thanks. So what advice would you give to a company looking at the regulations and goals they have to accomplish?
Yeah. And you're thinking, and there's two domains that I enjoy giving advice in, even if I'm not asked. One is how to think about automation, physical automation, robots, and virtual automation, AI, that's not in robots, what that means for your company. Because they relate to my energy advice. My advice there is an easy one. Don't think AI is a magic bullet that solves all problems, but don't be naive about how profoundly useful it can be in hyper-specific applications. And when new things come along, it's very difficult to figure out how to integrate them into your processes, supply chains or otherwise. So you have to form, special teams to figure out what to do and what not to do, in a sense, to get smart about it. But it is a big trend. So when big trends happen, you don't want to get behind the curve. So my advice in terms of the AI part and automation, physical automation, robots in the supply chain in particular, robots in warehouses, is this is a macro trend that you want to understand and get ahead of, or at least be in the wave. You don't have to be ahead of the wave. It's safer to be in the wave ahead of the wave, you may, if you get too far ahead of a wave, then it's not very good. On the energy side, we have governments all over the world, especially in Europe, but in the United States now too, in our states, that are passing laws and regulations that companies have a fiduciary duty to understand and follow. My advice is not to ignore those fiduciary duties, but again, similarly, to be realistic about what the macro trends are. So when we started, I said there's no energy transition. That doesn't mean that if you're a business and you're required either by law or by social license, let's call it, because politics matter. I'm just going to say again, I'm not saying we run roughshod over people's opinions, but your social license is to look more aggressively at non-hydrocarbon fuels, non-hydrocarbon behaviors, carbon footprint minimization. Doesn't matter what I think or you think about carbon dioxide and climate change. It's a fact that there are regulations and rules. That's a fact. So my advice is, when you look at those things, look at the fundamental macros. Do not build your business. Do not be naive around the belief that we're on the cusp of a major energy transition, because it will cause a shocking consequence to your operation. And of course, every business is energy dependent. And so I would phrase my advice this way: is people are preoccupied in the public policy sphere and politically with talking about climate risk, understanding your climate risk, which operationally distills to weather risk. I mean, and I'm not being facetious. Operationally, that's what it distills to. Whether you have storm, flood, drought, whether you think sea levels are rising or not, all these things these can be operationalized as fundamentally a weather risk, which you should understand. And if you think they're going to get worse, you should understand them. But there's a collateral risk, which is very real, what I call transition risk, and it's poorly studied. And this is related to my point. The macro matters. If government policies lead to energy shocks in terms of reliability or cost of the fuels you have to use to operate, you better understand how your business operates in an environment where reliability declines or availability declines, or prices are discontinuous. That is, keeping prices down by subsidy is you need to understand the extent to which the prices are subsidies dictated, because those are political events and they can change the stroke of a pen. You can't change the physics of combustion with a stroke of a pen. By that I mean the fact that it's cheaper to fuel a semi-trailer with diesel fuel is an engineering economic fact than an electric truck. But I can make with a stroke of a pen, it costs the same. But those are subsidies which are politically driven. In the real world of risk analysis, you want to understand the durability of those subsidies. If they go away, I'll use this as a simplistic example, and you're fully exposed in your business to operating vehicles that their operating cost was driven by a subsidy, not by underlying engineering economics, and that goes away with the stroke of a pen, you have a problem. You better do risk-adjusted thinking about that. And I think more businesses are doing that. This, of course, relates to the geopolitics, the supply chains from China, but I'm talking about a business. If I'm a business, I want to understand my operations and the energy features of it that are constrained by engineering economics or that are distorted by subsidies, which are political. One of the engineering economics do change with technology progress. Batteries will get better. Of course they do, but that's the range of the range of the improvements are knowable. There's no discontinuities coming in the next decade, right? The percentage rate of improvement is knowable. There are discontinuities that can come from the stroke of the pen political regulatory class. And we're seeing some of that already in Europe with some of the votes, the last vote, sort of the reaction, populist reaction. Some of that reaction is driven by high energy prices, as you know. And some of that's happened in the United States before, and it will happen again. Again, if I'm a business, I can have an opinion of whether that's good or bad. I may not like it. I might like it, whatever. You have to divorce your opinion on that from the underlying risk analysis. What happens if this political event changes and my artificial subsidies go away? What happens to my operation? You should understand that. And the inverse is what happens, if the politics make it illegal. For example, United States, 12 states, it will be illegal for the sale of an internal combustion engine, as it will be in a number of European countries. I'd sure want to risk adjust that, because it could go one of two ways. The physics of batteries are not going to change in the next 8 years, but the possibility that regulators and politicians will change the laws is a very high probability. So you want to sort of risk adjust what that means for your business.
Great. So what's some of the best advice that you've ever received?
Buy low, sell high for an investor.
Yeah, that's great. Easy.
And of course, I've often bought high and sold low. I do investing work to some extent. I used to write an investment newsletter, so I'm only being half facetious. When we wrote our technology investment newsletter, my colleague and I, some years ago, our goal was to find gems in the technology world, what's called the digital power report. So we looked at the pantheon of energy power technologies, from fuel cells to semiconductors like silicon carbide to make more efficient power converters, through to things like AI chips. We looked at the power features of those things, and trying to guess who was a good company and was it a good buy low, sell high. I would say, I'd separate it into two. It's just personal. I'm not going to talk about personal advice so much as business advice. The thing that I've learned over time about the business and the intersection of business and politics is not to give short shrift to, not be naive about the human factors on any engineering or business decision. By that I mean the nature of what people care about. So in an operating business, it's being aware of your employees. I mean, people have said many times, the most important thing you do is how you hire people. It's the quality of your team. The flip side to that is, when you're thinking about making forecasts in your business, we get preoccupied with economic metrics, and we get preoccupied with engineering metrics. I'm guilty of that, physics metrics. But the metrics that really are critical, not just from a moral perspective, but is in the world we live in, because we are humans. We're not irrational people. It's sad to say humans are irrational. No, they're not. Humans reason differently than computers. The word rational comes from reasoning. You have to understand how people reason. You have to understand human factors. So it doesn't matter I'm not talking about the computer interface. That's a human factor thing, but in planning. So the human factor side, the political side, if you like, is a human factor feature. And I think there's a lot of a naivete, and come back to the energy world. A lot of the things that policymakers expect people will put up with, even if they agree with you that we should do X. The X is obviously cut down your carbon footprint. Let's just say you've got a population, and polls show would agree, good idea. Polls show overwhelming majority, both in Europe and in the United States. U.S. less of a majority, but it's still a majority. And let's say good idea. Don't mistake that for the license to impose on people consequences that will have a huge effect on their lives. Human factor feature, in terms of convenience, how they can live their life, time for refueling, what things cost. Those human factor features of decisions are important for businesses and for policymakers to bring back in. And I'll admit, it's difficult to divorce that. You mean in your own head, you divorcing your political opinions about the human factors. You label the other people with different opinions as being, you pick a label that is sort of mildly insulting or really insulting. But if you're being analytic, you have to understand where they're coming from and why. The human factors really, in the end, you can't escape two things. I sort of have a rule of thumb. You can't escape the laws of nature, and the two ones that matter the most. The physics laws of nature you can never escape. You could pretend and you can hide with subsidies what they are, and you cannot escape the laws of human nature either in your planning. The laws of human nature are, of course, how people operate, their emotions, their conveniences, what they want in life. That affects businesses. So the advice that I got was really from I guess somebody I would call a industrial psychologist, and read a lot for reasons that are arcane. They're in my book too. My book has a lot about this aspect of forecasting. My book is a forecasting book, and it's animated by the intersection of those two, what I call laws of nature. That's a long answer to good advice, but you can say people matter. people matter. That's what it boils down to. People's opinions and emotions matter.
Definitely. And I'm gonna link your bio. I'm gonna link your work. I'm gonna link the journal you did yesterday. I'm gonna put all the work that I can find into the bio so people can search your book and find more information. The final question is there anything that I haven't yet asked you that you would have wanted to?
The subtitle of my book is The Roaring 2020s, right? The Roaring 2020s, named after the period in American history called the Roaring 20s, 1920s. And in the world, Europe followed the United States a little later. And the question I often hear from people when they see the subtitle is, it doesn't feel like the 2020s are roaring yet, in a positive sense. When do you think that will happen? Or do you still think it'll happen? And I still think it'll happen. Getting timing right of when the things start to unleash. The reason I subtitled that, it was originally going to be the lead title, The Roaring 20s. And then my publisher said, people will think it's about history and the jazz age and flappers and, and to which I said, that'd be fine. People will buy the book if they care about the jazz age. We are at a pivot in history, very much like the 1920s. There's a confluence of technologies that will animate economic growth and improvement in human well-being. By that I include healthcare and environmental metrics we all care about at lower cost far more easily than any time in a century. We made enormous progress in the latter half of the 1920 to year 2000. We had wars over that period. It's self-evident. Humans did not stop fighting and killing each other. I'm not naive. I write that in my introduction. But the question you didn't ask is, when will the roaring start? And I say the hints of it have already started, of an economic revival, which I think will drag reluctant Europe along with it. I worry that Europe is becoming senescent. I think what will save Europe, frankly, is that the technological revolution we're at the beginning of, the end of the beginning of the computing age, the cloud age, will probably rescue Europe from senescence, which I think would be wonderful. It would be very sad if Europe economically sinks, and it's in distress right now, broadly speaking, as you know. So if we don't kill each other first, which I think we probably won't. We've had wars before. We have hot wars right now. I think they get resolved, and I think we will experience within the decade an economic boom unlike anything since the 1920s. And I think the data show that the case. That's why I'm data driven. It's in my book. I think that's the case. I think that will go a long way to solve a lot of the problems of things that we want to solve, things that we want to do, fundamentally cost money. Unless we're wealthy and wealth is growing, we can't do those things, including all the things that I might disagree with. We can make mistakes when we're wealthy in terms of policy decisions. It's a very high consequence when you make a mistake when economies are stressed. So you didn't ask whether I think the economies are going to boom again or whether Europe survives. So I'm going to tell you the economies will boom again. And I hope that Europe will be dragged along by that boom, because a lot of the technologies, of course, are in Europe. It's not like the US is the only place of technology development. We may dominate, but we're not alone.
And will we get the emissions down?
Ultimately, yes, but not the amount and the timeframes anybody's talking about. If I were betting on CO2 emissions, it's easy to take the bet. They've been going up. They're still going up, and they're still going to go up, no matter how much money we spend on windmills, solar, and electric. It will make no difference. In fact, arithmetically, we already know this. The new coal plants that China is building now, just the new ones, when they're completed the next 2 years, 3 years, will add more CO2 emissions than Europe and the United States will reduce over the next 20 years. Just the additional coal plants. And that's just China, not India and Indonesia and Africa. So there's no amount of money that can be spent that will lead to CO2 emissions going down. That's just a technical fact. So pretending otherwise and showing PowerPoints that this will bend the curve down, this is PowerPoint land, not physics land. That's not how the world is working or where it's going. The data aren't there. The emissions are up. So my advice on that domain is for those who think that that has a consequence, right? If you think the consequences are negative, then this is the ascendance of a rational reaction, which is the adaptation, right? And resilience, where money should be spent on adaptation and resilience. If you think there are consequences that are negative, you should invest in technologies that improve resilience of our supply chains or our food systems. And that's a hold harmless expenditure, because even if you're wrong, adaptation and resilience are very good. They're inherent goods. Even Bill Gates has said what I just said, by the way. After the last COP conference, he pointed out that even if all of the goals and plans that everybody has imagined, that no one is doing, by the way, no one's doing what they claim. Only 3 countries like Gambia, I think Monaco and Morocco are doing are meeting their Paris Accord goals. No one's doing it. But even if everybody did it, as Gates said, in 2050, CO2 emissions will be higher and they'll still be rising. And if the world's gotten warmer, it'll still be warmer by essentially the same amount as it would have. Immeasurably different outcome based on the computer models. So he has said, since that's a fact, he didn't say don't stop doing all the other things, as you know. Since that's a fact, that's what the world is in fact doing, we should be serious about adaptation and resilience and about long-term changes in the energy infrastructures. And the long term is very different than the short term. Short term is 30 years. In the energy world, that's tomorrow. What you can build that can run for 30 years, we know how to build today. If you want fusion and room temperature superconductivity, biofuels that are cheaper than hydrocarbon fuels, those all require revolutions in physics and chemistry, all of which are imaginable, none of which exist yet. All of which could exist in the next, several decades. It could be operationalized in the decades that follow. But that requires money spent on R&D, not subsidies. And this is a very different shift politically. The politics are to subsidize yesterday's technologies. To end on an obnoxious note, we are subsidizing yesterday's technologies instead of investing in tomorrow's revolutions. And every dollar spent subsidizing something that was invented 50 years ago or 30 years ago or 20 years ago is not going to make a whit's bit of difference to the future of carbon dioxide emissions. You want to change the game, you need really radical new science. Bill Gates said you need miracles, and he didn't mean that in the sense of impossible. I wrote a paper called Magical Thinking. It's not magical to think you can have miracles. Miracles are the discovery of nuclear fission was miraculous. The discovery of the photovoltaic effect was miraculous. Lithium chemistry is literally miraculous compared to lead chemistry for batteries. It's an incredible, the discovery of rare earth magnets was a miraculous discovery. So that's what Bill Gates is talking about, those classes of miracles. Those are hard to come by. We're not focused on that in the political debate. So it's a long way of saying I would take the bet and the data. CO2 emissions have been going up. They're going to keep going up. If you don't like that, okay, I understand. I mean, I get the arguments fully. I appreciate them. I'm not intellectually sympathetic with them because I know what we can do about it, which is adaptation and resilience, which takes money, which takes wealth. And the wealth comes from unleashing these next revolutionary technologies. And it's particularly in the cloud and AI and automation and robotics. You want mining to be more efficient and cheaper, for cheaper copper, you're going to need a lot of robots and a lot of AI. And a lot of diesel fuel too, by the way, for a long time.
Definitely. Thank you so much, Mark, for this conversation.
My pleasure. Thank you for having me on. And good luck with your podcast. I hope it has a knee in the proverbial curve and your audience takes off and you become the sage of the internet airwaves.